Hello, my name is Morgan. I'm a junior studying mechanical engineering with the privilege of doing research with Professor Jeff Squire. Today I will be talking about measuring metal 3D printing, thermal topography in situ via passive multi-wavelength spatial frequency modulated imaging. Metal 3D printing is a new frontier for manufacturing by allowing for a wide variety of part geometries and materials that are hard to utilize in traditional manufacturing. With laser powder bed fusion, exotic materials like Inconel and titanium become far easier to manufacture. These new capabilities make the technology an area of interest for many industries. Medical and aerospace companies are especially interested in the unique capabilities of metal 3D printing. However, these companies' applications require rigorous quality control. Unfortunately, the process repeatability is poor and inconsistent. Consider the Adam Savage Iron Man suit developed in collaboration with mines. It required each part to be printed 6 times to create just one full suit because the other 5 parts would likely fail. This inconsistency is due to a variety of thermal effects taking place at the part surface that cause porosity and warping of the printed part. These defects drastically reduce the structural integrity of the part. For critical applications, parts are inspected after the printing process using a variety of expensive and often radioactive metrology techniques. There is a need for quality control tools in the metal 3D printing industry, especially those that allow the printer to correct mistakes in situ. An ideal process control for metal 3D printing would be able to evaluate temperatures around the laser interaction zone. However, capturing this thermal information via contact thermometer is not possible. Blackbody radiation provides an alternative. Everything in the universe emits light in a Boltzmann distribution with a central wavelength according to its temperature. Using the spectrum of light emitted by an object, the temperature can be determined. This is the same technology used in the now ubiquitous contactless IR thermometers. By taking a spectrum of emitted light from individual locations across the part, thermal topography can be determined. Measurements must be taken rapidly across the surface of the part. Spatial frequency modulated imaging, also known as SPIFI, is here to help. SPIFI is a novel imaging technique for evaluating points along a line that works by assigning a unique frequency to each point on the line. Imagine a line of musicians, each playing a different note depending on their location in the line. A talented composer could pick out the volume of each note from the individual musicians while they are playing. SPIFI works on the same principle by picking out the locations on a line using a single detector by reversing the frequencies and their magnitudes using the fast Fourier transform. The GIF shown is the SPIFI modulation of a flat top beam with differences in frequency along the masks shown. The masks shown on the top are 2 methods of modulating the frequency along the length of the line cursor. SPIFI generally works by taking a continuous source, such as a laser, and modulating the source to create a frequency relation. The figure above demonstrates how this is normally achieved. However, the blackbody emission needs a SPIFI signal applied to be able to use the frequency to make a statement about the location of the thermal profile. Enter passive SPIFI. Passive SPIFI turns everything around by making the imaging plane and its associated blackbody radiation from heating the illumination source. The blackbody radiation is relayed to a slit to make the imaging area a line appropriate for the frequency modulation, and then a SPIFI mask applies the frequency components along the line. Once every spatial location has a frequency, the signal is sent through a diffraction grating to separate the wavelengths of the light in a space so they can be evaluated on separate high-speed detectors appropriate for the wavelength. The resulting signal from each detector will have a fast Fourier transform applied, and then the resulting magnitude ratios at each spatial location will be fit to a Boltzmann distribution to determine the thermal topography. However, trying to achieve all this in one jump would be rather challenging. Passive SPIFI has not been done before, and adding multiple wavelengths, as required for making thermal measurements, causes complications in the optical design. Additionally, the 400-watt laser used to melt the metal is dangerous. Thus, for initial testing, we decided to create an approximate source using an infrared LED. Using the LED means that the entire system can be tested repeatedly at the same wavelength. The figure shown above is a preliminary optical system diagram modeled in Zmax for a single wavelength. The light emitted by the LED is first collected by the same lens used to focus the fusing laser. Next, it is transmitted through a dichroic and focused back onto a slit. The slit cuts out extra information What is left is relayed to the mask to be modulated and then focused onto a detector. Despite the pandemic, we've been working hard on the development of the passive SPIFI system. We've started to get SPIFI traces back onto our detector. The beat pattern shown is caused by the interactions of different frequencies produced by the mask and is a great indicator that everything is working correctly. There are many steps left to prove out the technology. First, while the current SPIFI mask does a good job of demonstrating that non-coherent light can produce a SPIFI signal, it struggles to reproduce correctly with the fast Fourier transform due to defects in the mask. Replacing the mask with an updated version will address these issues. Additionally, the current setup has the SPIFI mask and slit trying to share the same imaging surface, further reducing optical performance. Addressing these issues will allow for a clear line image of the LED. Once the setup works for an LED, a dichroic can be added in to allow for imaging while a simulated 3D printing surface is being heated by the high-power laser. By using the blackbody radiation from the heated surface at a single wavelength, the technique is mostly validated. Finally, the optical system will need to be adjusted for multi-wavelength operation and thoroughly tested. In conclusion, passive SPIFI provides a new technique for evaluating thermal topography during the metal 3D printing process. Validating passive SPIFI in a single wavelength is the first major step. With more hard work, this technique can be fully realized to enable high-speed, high-resolution thermal measurements. Thanks for watching.